In this video, I will be discussing about inverse trigonometric substitution. Basically, this is a substitution technique. And we know that effective substitutions in integration are often suggested by the form of the integrand. Now, this technique is especially useful in the evaluation of integrals that involves rational functions of sine x or cosine x or both. This technique consists essentially the substitution of the inverse function x is equal to 2 arctangent z. So your variable of integration x will be substituted by this 2 arctangent of z. And if we are going to find the derivative of this x, we have dx, which is equal to 2 because 2 here is a constant, times the derivative of arctangent z, which is dz over 1 plus z squared. So this is the differential of your x. However, I can rewrite this substitution by dividing both sides of the equation by 2. So this is x over 2, which is equal to the arctangent of z. And taking the tangent of both sides, we have tangent of x over 2, which is equal to z, because tangent and the arctangent are inverses to one another. So we have only z here. So by this trigonometric relation, we can draw a geometrical representation of this. Now, we know already that tangent is the ratio between opposite over adjacent. So if this is our argument here, which is x over 2, based from this trigonometric function, we can place z to the opposite of this reference angle of x over 2. And since we don't have a denominator here, the denominator is understood to be 1. So we place 1, which is adjacent to the side of the reference angle x over 2, so that the tangent of x over 2 is opposite z over adjacent of 1, which is equal to z. So therefore, we can find the third side, which is the hypotenuse in this right triangle. So using the Pythagorean theorem, this is equal to the square root of 1 squared, which is 1, and the square of z, which is z squared. So based from this drawing, we can easily find our sine function of x over 2. And the sine function of x over 2 is opposite z over the hypotenuse of the square root of 1 plus the square of z. And also we can find our cosine function here, which is cosine function of x over 2, which is equal to the adjacent 1 over the hypotenuse, which is the square root of 1 plus the square of z. But since looking at this angle, because this is half of x, we can use our trigonometric identity, which we've learned even when you were still in high school, which is the sine 2 theta, which is equal to 2 sine theta cosine theta. So applying this double angle identity here to this one, we have the sine of twice of the angle x over 2. We have 2 times the sine of the angle x over 2 times the cosine of x over 2. And we know that the sine of twice of x over 2 is just the sine x. And also, we know that sine of x over 2 is this one here. So this is 2 times z over the square root of 1 plus the square of z. And this is multiplied by the value of cosine x over 2, which is this one. 1 over the square root of 1 plus the square of z. So simplifying our equation here, we have sine x, which is equal to 2z over the square root of 1 plus z squared times the square root of 1 plus z squared, that makes the whole exponent of 1. So this is 1 plus the square of z. So this is now the value of sine x. Also, we can use our identity, our double angle identity, for the cosine function. So cosine 2 theta is equal to cosine squared theta minus sine squared theta. So applying this double angle identity for cosine, we have cosine of twice of the angle x over 2. And this is equal to cosine of x over 2 quantity squared. And this is also subtracted by the sine of x over 2 quantity squared. And then simplifying further, we have cosine of x, which is equal to the square of cosine x over 2. But cosine of x over 2 is equal to 1 over the square root of 1 plus z squared. So we need to square this one, and then this will be subtracted by the square of the sine x over 2, which is z over the square root of 1 plus z squared here. So we need to square this one. Now, squaring the numerator, which is 1, is still equal to 1. And squaring this square root, we have 1 plus z squared minus z squared all over 1 plus the z squared here. And then combining these two fractions which are similar, we have cosine x, which is equal to 1 minus the z squared over 1 plus z squared here. So basically, this substitution will employ this value of sine x and this value of cosine x together with our dx here. And to illustrate this one, let's solve our example number 1. So what is the integral of dx over the quantity 1 minus sine x minus cosine x? So basically, the idea is to substitute our dx by this expression here, and for sine x and cosine x with these expressions here. So we have the integral of dx over the quantity of 1 minus sine x minus cosine x. We have this integral of 2 dz over the value of 1 plus z squared, which is this one here, all over 1, which is this one, minus the sine x. And we know that sine x is 2z over 1 plus z squared minus the cosine x, which is 1 minus z squared over 1 plus z squared here. And simplifying it further, we have the integral of dz over 1 plus z squared, which is multiplied by 2, will be divided by this trinomial here, but we will combine them into just one fraction with the LCD of 1 plus z squared. So this one becomes 1 plus z squared, and this one becomes 2z minus the quantity of 1 minus the square of z here. Now, simplifying it further, we have this numerator, which is 2dz over the denominator of 1 plus z squared times the reciprocal of the denominator, which is 1 plus z squared over this one, which is 1 plus z squared minus 2z minus 1 plus the z squared here. Now, looking at the numerator and the denominator, we can see expression that can be cancelled. So we have 2dz, which is divided by 2z squared, because we have 2 z squareds here, but the 1 and the negative 1 cancels each other, and this will be subtracted by 2z. Now we can see that we can factor the 2 in the denominator, which is common to the two terms. So we have 2 times z squared minus z, so that this 2 in the numerator and this 2 cancels each other. So we have our answer as the integral of dz over the value z squared minus z. But since this is a fraction which is a proper fraction, so if I may write this one as 1 over z times z minus 1, by factoring z from this both terms, we can decompose this fraction to a sum of its equivalent partial fractions. And I know that you learned this one from your pre-calculus, how to decompose a proper fraction. So if I may write here 1 over z times z minus 1, I can decompose this one to its equivalent sum of its proper fraction as a over z plus b over z minus 1. So the skill that we need here is decomposition of proper fraction to its equivalent partial fractions. So if I multiply both sides of the equation by the LCD, which is z times z minus 1, you will have just 1 at the left, because this 1 and this 1 cancels each other. So we have a times z minus 1, and this is added to b times z here. Now, the next goal is to find the values of a and b. And to find the value of a and b, we need to eliminate first b. And b can be eliminated if you set your z equal to 0. So if your z is equal to 0, then the equation becomes 1, which is equal to a times 0 minus 1 plus b times 0. So therefore, your a is multiplied just negative 1. Hence, your a is equal to negative 1. So this is now the value of a. So how about b? We can find b if we can eliminate a. So how do we eliminate a? If we have a multiplier of a which is equal to 0. And this can be 0 if your z is 1. So if your z is equal to 1, then the equation becomes 1, which is equal to a times 1, because if your z is 1, so we have 1 minus 1 plus b times 1. Now here, our a is multiplied by 0, and this is equal to b. Hence, 1 is just equal to b. Therefore, we have the value of b now, which is equal to 1. So therefore, we can write this proper fraction as a sum of two partial fractions, which is a over z plus b over the z minus 1. And we know already the value of our a and b, because the value of a is negative 1, and the value of b, which is 1. And then applying the property of integrals, that the integral of a sum is equal to the sum of its individual integral. So this is minus the integral of dz over z, if you distribute the z here, plus the integral of dz over z minus 1. And we know that the integral of dz over z is ln z, plus the integral of dz over z minus 1 is ln of z minus 1 plus the constant of integration c. And we can rewrite this one into just one logarithm by setting the z minus 1 as our numerator and this z here as our denominator because it has a minus sign. So this is the natural log of z minus 1 over z. And simplifying it further, we have the natural log of 1 minus 1 over z plus the constant of integration c. And we know already that the value of z is tangent of x over 2. So here we will have 1 over tangent of x over 2 plus the constant of integration c. So therefore, our answer is equal to the natural log of 1 minus the cotangent of x over 2 plus the constant of integration c. So this is now our final answer for this example number 1. Now let's proceed to our example number 2. What is the integral of dx over the sum of sine x and tangent x? Now, we notice that this is a rational function involving sine x and tangent x, but actually we can rewrite tangent x there in terms of sine x and cosine x. So we have the integral of dx over sine x plus sine x divided by cosine x there. So therefore, this is a rational function that involves sine x and cosine x. So we can use the inverse trigonometric substitution here using the one that we derived in the previous board, that z is equal to the tangent of x over 2. So solving for x, we need to take the arctangent of both sides and then multiply both sides of the equation by 2. And the resulting value is x, which is equal to 2 times the arctangent of z. And we derived it already that the derivative of x is 2 dz over 1 plus z squared. And also we have the value of sine x, which is equal to 2z over 1 plus z squared, together with our cosine x, which is equal to 1 minus z squared over 1 plus z squared here. So substituting our value of dx, our value of sine x, our value of cosine x to our integrand, we have the integral of dx, which is 2 dz over 1 plus z squared. And this is divided by sine x, which is 2z over 1 plus z squared. So we have here 2z over 1 plus z squared. And this is added to, again, our sine x, which is 2z over 1 plus z squared, divided by the value of cosine, which is this one, 1 minus z squared over 1 plus z squared there. Now, simplifying our denominator, we have the integral of 2 dz over 1 plus z squared divided by this 2z over 1 plus z squared. And this is added to the quotient of these two fractions. So to find the quotient is to multiply our numerator by the reciprocal of the denominator. And the reciprocal of this is 1 plus z squared over 1 minus z squared. So we can cancel this expression here. So what remains is the integral of 2dz over 1 plus z squared divided by our denominator, which is 2z over 1 plus z squared. And this is added to the remaining terms here. We have 2z over 1 minus z squared. So combining these two fractions in the denominator, we have the integral of 2dz over 1 plus z squared. This is divided by these two fractions having the LCD of 1 plus z squared times 1 minus z squared. And if this one will be divided by 1 plus z squared, the result is 1 minus z squared, and that will be multiplied to our 2z in the numerator there. So this 2z also will be multiplied by the quotient when this one is divided by 1 minus z squared. And the answer is 1 plus the z squared there. So simplifying it further, we have the integral of 2dz over 1 plus z squared. This is divided by the 2z minus 2z cubed, because this is the result when you distribute 2z to this binomial. And distributing also 2z to this binomial, we have plus 2z plus 2z cubed, and this is divided by the product of 1 plus z squared and 1 minus z squared. And we notice that this term and this term cancels each other. So we have the integral of 2dz over 1 plus z squared, and this is divided by the remaining term 2z plus 2z is 4z over these two factors 1 plus z squared times 1 minus z squared there. And we know that to simplify is to multiply our numerator, which is 2dz over 1 plus z squared, by the reciprocal of our denominator, which is 1 plus z squared times 1 minus z squared there. And this is having a denominator of 4z. So we can cancel this term with this term here. So we have the integral of 2dz times 1 minus z squared over 4z. But we can cancel one of the 2 here with the 2 in the numerator. So we have 1 minus z squared dz over 2z there. And then we can factor out the constant outside the integral symbol. We have 1/2 of the integral of 1 minus z squared over z dz. But we can divide these two terms by this denominator z. So we have 1/2 of the integral of 1 over z minus z here. And then applying the properties of the integrals, we have 1/2 times the integral of dz over z. and this will be subtracted by 1/2 of the integral of z dz, because the integral of a difference is a difference of their individual integrals. And we know that the integral of dz over z is the natural log of z, and also the integral of z dz is z squared over 2 plus the constant of integration c. So therefore, our answer is 1/2 of the natural log of our z, which is the tangent of x over 2, because that is the representation of z. And this will be subtracted by 1/4 of the square of our z. And the square of z is tangent squared of x over 2 plus the constant of integration c. So therefore, this is our answer for example number 2. Now let's proceed to our example number 3. What is the integral of dx over the sum of 5 and 4 sine x? Now since this is a rational function that involves a sine function, then we can use the inverse trigonometric substitution here, which is z that is equal to the tangent of x over 2. And solving for x, we know that is 2 times the arctangent of z. And finding the derivative of your x, we have 2 dz over 1 plus z squared. And also, we know what is our sine x here. Our sine x is 2z over 1 plus z squared. So we can substitute our dx and our sine x here in our integrand. So we have the integral of dx, which is 2 dz over 1 plus z squared. So instead of writing dx, I will write its equivalent expression, which is 2 dz over 1 plus z squared. And this is divided by 5 plus 4 sine x. And our sine x is 2z over 1 plus the z squared. So simplifying our integrand, we have the integral of 2 dz over 1 plus z squared. We can combine the denominator. We can simplify the denominator as 8z over 1 plus z squared to multiply 4 and 2z. And then we can combine the denominator here by finding its least common denominator. And the least common denominator is 1 plus z squared. So 1 plus z squared when divided by 1 is 1 plus z squared. So 1 plus z squared will be multiplied to the numerator 5. And then this 1 divided by 1 plus z squared is 1. So times 8z, that is 8z only. And then we can apply the law of division by multiplying the numerator by the reciprocal of the denominator. And we know that the reciprocal of this is 1 plus z squared over 5 plus 5z squared. And this is added to 8z. And we notice that this expression and this expression cancels each other. So we have the integral of 2 dz over 5z squared plus 8z plus 5. And we notice that this is a quadratic expression. So factoring this 2 outside the integral symbol, we have 2 times the integral of dz over 5, if we factor out the 5 as the constant of the trinomial, we have z squared here plus 8 over 5z plus 1 there. So that I can still factor out the denominator of 5 outside the integral symbol. So we have 2/5 times the integral of dz over z squared plus 8 over 5z, and then we need to add one term there to complete this trinomial. And what is that term? That third term that we need to add is just the square of the half of the second term. So what is half of 8 over 5? Half of 8 over 5 is 4/5. So this is 4/5 quantity squared. So this is the one that we need to add to this expression to make it as a complete square trinomial. But of course, you will be asking, where did I get this square of 4/5? I need to have a balance by subtracting also square of 4/5 there. So simplifying our integrand, we have 2/5 times the integral of dz over this perfect square trinomial, and that perfect square trinomial can be written as z plus 4/5 quantity squared, and this 1 minus the square of 4/5, we have plus 1 minus 16 over 25. And performing simple arithmetic, we have this denominator, which is z plus 4/5 quantity squared. We have this 1 minus 16 over 25 as one fraction here. So this is 25 minus 16. And we know that 25 minus 16 is 9. So this is 9 over 25. But this 9 over 25 can be expressed as a square. So we have a denominator of z plus 4/5 quantity squared plus 3 over 5 quantity squared also. So if you let your a be equal to 3/5, because we have a constant of 3/5 here, and our u there, which is z plus 4/5, we notice that our du here, if you get the derivative of z, is only 1. So we have 1 dz, because the derivative of 4/5 is 0. So substituting these representations of a, of u, and du here, we have 2/5 times the integral of dz, and dz is du here, and this will be divided by this square of z plus 4/5, which is u. So this is u squared plus the square of your 3/5, and 3/5 is a there. And we know how to integrate this one, because this is a form that is familiar to us, that the integral of that du over u squared plus a squared is equal to 1 over a times the arctangent of u over a plus the constant of integration c. So substituting back the values of a and u, we have 2/5 times 1 over a, which is 1 over 3/5 here, and multiplied by the arctangent of u, which is z plus 4/5 divided by our a, which is 3/5. And this will be added to the constant of integration c. So simplifying it further, we have 2/5 times 1/3/5 is equal to 5/3 times the arctangent of our z plus 4/5, which is 5z plus 4/5, and this is divided by 3/5, and of course this is added to the constant of integration c. So we have 2/3, because this 5 and this 5 cancels each other, times the arctangent of 5z plus 4/3, because this denominator of 5 cancels with this 5 here. So this is added to the constant of integration c. So our final answer is 2/3 times the arctangent of 5z, but our z is the tangent of x/2. So this is 5 times the tangent of x/2 plus 4 over the denominator of 3. And of course, this is added to the constant of integration c. So this is now our answer for this example here. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.